יותר מדרגה.
אז זה לא בדיוק שזה קבוע, אבל זה יותר כמו, אם אני עכשיו אכפיל את הכל, אז אני יכול כזה, לבלוע את הקבועים השפליים בתוך ה-W, חושב שזה הקשר. זה דומה למה שהיה לנו בפרספטרון ודומיו.
כאילו בהכשרה 3 שנים, אבל בקבע נשאר גם את 7.5 שנה.
באמת שכאן היה, אחראי כאילו אלקטרו, לא מעט על אלקטרו.
אחראי על מה?
כאילו, לפני או כדי...
Okay, good afternoon. We continue our discussions on correlation. We will finish it today and hopefully start a new topic. So, I would like to remind you the setup that we are considering. We looked at several examples. We have neural responses which we characterize by the difference. Actually, what we care about is the difference in the mean response of each neuron in two conditions, theta 1 and theta 2. So we call that GI. And this is, again, the mean in the difference of the responses. And then we had the covariance matrix, Cij, and we considered a specific form of the covariance matrix, which is given by this structure. So when alpha is 0, the neurons are uncorrelated, and when alpha is equal to 1, they are fully correlated. And we assume that the noise is independent of the stimulus, and that furthermore the responses are Gaussian. And then we considered some examples, identical neurons or two populations of neurons that have opposite responses, and we saw how the discriminability depends on the number of neurons, and we saw some interesting things. So maybe I'll just remind you of those results, and then I want to discuss an interpretation of these results in a geometric manner. So I'll quickly go through the examples that we went through. So one was n identical neurons, and I will not write all the details. It means that all the GIs are the same, and then we got that the d prime optimal square is ng square over a. So the larger the number of neurons, the better the discriminability.
When you say identical, you mean
that the properties are identical. I do not mean that they produce the same output. That's the fully correlated case. So yeah, my terminology when I say identical, I mean they have the same tuning curves or the same responses, mean responses. But the noise, so here it's n identical independent actually, in this example. The noise is completely independent in the different neurons. And then we considered n identical but partly correlated. I'll put partly in parentheses because as one particular case they can also be fully correlated. And then what we got for the discriminability was d prime square opt is g square over a times n. You know what, I will not write it. I will just write that when alpha is equal to 0, we of course get the same result as in 1 because that's the uncorrelated case. But if alpha is smaller than 1 and larger than 0, we get that d prime square approaches g square over a alpha when n goes to infinity. So that's the most important result, that once the neurons are somewhat correlated, we cannot longer increase our discriminability indefinitely by increasing the number of neurons. The discriminability saturates. But then we considered also a case where we had two populations with opposing responses, and we got something quite different. What we got is that is it okay if I write here? Here, yeah. D prime square was equal to g square n divided by 1 minus alpha. So now we rescued this the dependence of n on n that we had in the uncorrelated case. Even if the neurons are correlated, the discriminability increases when we increase n, and not moreover, it's actually better to have correlations. If alpha is larger, we're doing better. So now I want to take all these results and think about them in a somewhat geometric manner and interpret them, what is going on. And okay, so geometric interpretation. So what I want to start is by thinking about just a case where we have two neurons. And let's just try to plot the distribution of their responses in our model. So this would be neuron 1, and this will be neuron 2. And let's think first about the uncorrelated case, uncorrelated case, and about scenario 1. So scenario 1 is the one where the responses, the mean responses, are the same. So if I want to just plot on this plot the mean responses of the two neurons, how would they look like in the two conditions? In the case of what I called identical neurons, and I want to plot a dot here that represents the mean responses of these two neurons, what can I say? What will they look like? They will be on the diagonal because the two neurons provide the same response, mean response, in the two conditions. So there will be 2 points on the diagonal that represents the mean responses. Okay? And now, but the neurons are variable. The responses are variable. So I want to depict graphically the distribution of responses of each neuron. So let's take the condition, say that this is the response to theta 1, let's say, and this is the response to theta 2. And now I want to consider first the case where the neurons are independent. So how will the but they have the same variance. So how will the distribution of responses look like conditioned on theta 1? It will be centered around this point. And what is it? What kind of distribution is it in our model? It's a normal distribution. It's a two-dimensional normal distribution. So if I would draw, I cannot draw, I would need another dimension to draw the probability, but if I draw just a line of equal probability, it will be some kind of circle, right? And then clearly, when we want to discriminate between the two conditions, we will put a separating line here. If we see the response to the two neurons, and if it's beyond this line, we'll choose this condition. If it's below this line, we'll choose this condition. So this graphically represents the case where the two neurons are uncorrelated with in red. I want to also draw on this on the same plot how would the distribution of responses look like if the neurons are fully correlated? So how would it look like if they're fully correlated? Yeah, it will be a distribution that slides only on this line. And so I don't know exactly how to draw it. Strictly speaking, I should just put like two dots here to represent two positions of equal probability. But what I mean is that like the neural responses are spread on a line. In fact, if we make the neurons more and more correlated, it's always a Gaussian distribution, and the points of equal probability are an ellipse. And this ellipse shrinks in this dimension as we increase the correlation of the neurons, and when alpha approaches 1, it becomes like a line. Okay, so this is the fully correlated case. Fine, this is just two neurons. We'll discuss in a moment what happens when we add more neurons, because this is what we really want to understand, the dependence on n. But I want to stick for a moment with two neurons, and now draw the same thing for the case, for this case. So this is scenario 3, populations with opposing responses. So this is actually scenarios 1 and 2. Let's call it 2, because scenario 1 is a subcase of scenario 2, right? So this is scenario 2, uncorrelated and fully correlated, and let's now consider the scenario 3. I did not write yet. It's somewhere in between, so the distribution would be an ellipse. I did not write. I will go back to that later. Okay, so now let's talk about case 3. So I still have two neurons, neuron 1 and neuron 2. And let's draw this diagonal. Where do the responses look? So let's assume that, remember, GI was defined as the difference in the responses of the two neurons in the two conditions. So let's imagine that on average, like the sum of the mean of the responses for theta n1 and theta 2 lies still on the diagonal, but now G is positive for one neuron and negative for the other neuron. So what does that mean for the neural responses in the two conditions? So they will not, if one neuron increases its response, the other one decreases its response. So we will not remain on the diagonal, and so it will look like this. The two conditions will look something like this. Okay? One neuron responds more, the other neuron responds less. And so I could still draw the distribution of responses in the two cases. And you see that you can appreciate that for the uncorrelated case, it really doesn't matter that the points are here or here versus here or here. But for the correlated case, fully correlated case, it's different, because for the fully correlated case, the noise puts us along this line. So in fact, you can see that while for the uncorrelated case, the probability of error will actually be the same in this condition and this condition. It's a probability of crossing the separating line between these 2 points, which will actually turn out to be the same in both of these cases, this one and this one. For the fully correlated case, what is the probability of error here? 0. The noise, if we observe a response condition on theta 1, we can always tell for sure if it came from this response or from a similar response here. Okay? So this was just 2 neurons. Uncorrelated and correlated. Now, if the neurons are partially correlated, then this circle will be squeezed into an ellipse. We will still have a probability of error. We'll discuss that in more detail later. Okay? Now what I want to discuss is what happens when we have n neurons. So now I'm going to do something slightly artificial, which will be slightly artificial for this case. It will be more clear for this case, which is I'm going to just split my neural responses into our neurons into 2 groups. One group with n over 2 neurons, and the other one also n over 2 neurons. And in this case, I just do it arbitrarily. In this case, from the start, we had the 2 groups. We had one that responds more. Our setup of the example was that half of the neurons increase the response, half of the neurons decrease the response. In this case, I'll just artificially divide the neurons to 2 groups. And what I'm going to draw here, so in principle, if I would want to draw the neural responses, I'd need to draw a point on an n-dimensional space, but I'll split my neurons into 2 groups and draw the mean response from one group and the mean response from the other group as a 2 axes. So mean, this will be mean activity in group 1, let's see how they note it here. Yeah, group 1. And this will be mean response in group 2. Mean I mean average, let's call it average. Averaged, meaning that I take the responses of all the neurons and just take the average. Average response. So, so the points, these 2 points, will remain the same when I have n neurons or n over 2 neurons in each group as opposed to 1 neuron in each group, because it's the average. So we'll have these 2 points in exactly the same place. But what can I say? Let's think about the uncorrelated case. What can I say about the distribution, the variability of this around this point on a trial-by-trial basis? So what is the variability around this point? Is it the same as here, or is it different?
Much smaller.
Okay.
By
By
a factor of
a factor of what?
n over 2.
No.
Talking about
The standard deviation? Standard
So
deviation?
the square root.
Right. So when you average n identical variables, the standard deviation goes like 1 over square root of n. And so what I should draw here is a circle which has a smaller radius. And the radius is smaller by a factor of order square root of n. Square root of n over 2, to be more precise. Okay, so you see that, so this radius, proportional to 1 over square root of n. So as I add more and more neurons, and if I just perform the discrimination by looking whether our responses lie below this separating line or above the separating line, if that's what I decide to do, you see that I will improve as n n increases, and you can see how it will improve. Now, in the fully correlated case, what's happening? I have n over 2 neurons instead of n. What happens to this line? So I averaged n over 2 neurons, which on a trial-by-trial basis, each one of them gives the same answer. They have the same noise. So nothing happens, right? The average of n over 2 variables that give the same answer is just like the value, the output of one of them. So in the fully correlated case, I still have the same, let's try to draw it exactly the same, I still have the same distribution here as I increase n. So we gain nothing. So this is what we discussed. We discussed this as the first example that you know, we add more and more neurons, and we don't gain anything. Our probability of error remains the same. Because again, the average of, if the neurons are, if I have n over 2 neurons that just spit out the same answer on each trial, then the average of them is just like the answer, like one of them. So n of 2 of these types of neurons is just like one neuron. Okay. So now if we plot the same thing on the case where the G's are different, you can see that we have these 2 points. And as n increases in the uncorrelated case, we improve because the radius of this blob becomes smaller. In the fully correlated case, we don't improve at all. As we increase n, we don't improve the standard deviation, but we don't care because it just doesn't affect our discriminability. Okay? So this is, so what we discussed so far is that why do we improve here, and why for 2 populations with opposing responses we always improve, that's the red, and when alpha is equal to 1 we actually have a discriminability, this d prime square is infinity always, regardless of n. What is more subtle is to discuss finite alpha, which we haven't done yet. We discussed, alpha which is larger than 0 and smaller than 1. This is a partially correlated case, right? We haven't discussed it. We just in this plot looked only at the fully correlated and the fully uncorrelated. So let's discuss a little bit the partially correlated case.
Can I ask something?
Yes.
I don't really understand why you drew both on the opposing responses. The one,
Yes.
the point beneath the diagonal, it doesn't seem like it's decreasing the firing rate, but increasing less.
By definition, okay, so by definition, what I didn't write everything down explicitly, but by definition, we had 2 groups, and with one of them, GI is plus G, and in the other one, GI is minus G. Let's just consider the case of 2 neurons first. Your question applies also to 2 neurons, or also to any? To 2 neurons. So for 2 neurons, we have one neuron that increases its response, its stimulus theta 2 relative to theta 1, and the other one decreases its response. So I'm just saying, let's imagine that the mean response for theta 1 and theta 2 lies on the diagonal. It doesn't matter. We could have put it somewhere else. I know that when one neuron increases its response, the other one decreases, and that's why I plotted the point here. And then when one neuron decreases its response, the other one increases. So in other words, theta 2, the response of neuron 1, this was neuron 1, this is 1 and this is 2. Okay, we can look here. The response of neuron 1 minus the response of theta 2, sorry, the response of neuron 1 for theta 2 minus theta 1 is positive, and it has the opposite sign. Is that okay? Yeah. Okay. Now, what is it? Okay, so now I want to discuss a little bit the partially correlated case. And I need to go back to this covariance matrix. And so I want to provide you some way to think about this covariance matrix, what it actually means. So we have this covariance matrix, which is A times 1, 1, 1, 1, 1, alpha, alpha. Now, I claim that you can think of a Gaussian set of Gaussian variables that have this covariance matrix in a very simple way. You can think about them, so all this is a covariance matrix of Ri, right? So let's think for a moment about the following model. Suppose that Ri is equal to Fi, which is their mean, plus some variable Xi, which is random, which is chosen independently and normal distributed. So in each neuron, I draw the response by taking the mean response, add to it some noise which is independent in the different neurons, and then I add to all the neurons some other noise. Let's call it Xi 0, which is the same for all neurons. And normally distributed. I claim that since this set of Ri's are all jointly Gaussian distributed, okay, in this model, and that if you will calculate what is the covariance matrix of these neurons, you will get exactly a covariance matrix of this structure. There will be a part of it which, so in the case where Xi 0 has 0 mean, where this part has 0 mean, we're in the independent case, right? The noise is independent in all the neurons. In the case where this has 0 mean, the neurons are fully correlated, right? Because the noise part in each one of the neurons is the same. So you can really think about this covariance matrix as coming from noise that has two components. One component is independent in all the neurons, and one component is shared by all the neurons. Once you understand that, you can understand what will happen to this covariance to this circle as you increase, in the partially correlated case, as you increase n. So first of all, this circle is an ellipse, because if alpha is smaller than 1 and larger than 0, this circle is an ellipse. But you can think of this ellipse as coming from two parts. It's coming from a part which is the independent noise, which is actually a circle, and a part which is this part, which is the shared noise, which is noise which just lies on this line. And the sum of them has a distribution which looks like a Gaussian, which is an ellipse. And now when we increase n, what will happen? When we increase the number of neurons, the part which is the isotropic will shrink, just as much as it was shrinking from here to here. But the part which is shared, this part will not shrink. Okay, so for that reason, if our 2 points lie here, we will improve as we increase the number of neurons. We will improve because this ellipse, the part of it which is like a circle, will shrink, and we will remain at the end with a line which has a somewhat smaller variance than the variance of the two components, the shared component and independent component. So we will improve, but we will saturate. Our noise eventually, when n is large, will become on this line and will not change anymore when we increase the number of neurons. If we look at this picture, then we have the same structure of noise, and as we increase the number of neurons, this ellipse will shrink into a line. The line will not shrink anymore. We'll reach a fully correlated case, but we don't care. That part of the noise a noise that lies on this diagonal doesn't affect our discriminability. So what you see from these examples that it really matters what is the structure of the noise. As we increase the number of neurons, we might shrink this cloud in some directions. Maybe in some direction we don't shrink it anymore, and now the directions that remain, it matters whether they are affecting our discriminability or not. Okay? So now I want to discuss one more example, which is like along the lines of what I did yesterday, 1, 2, 3. I want to discuss one more example. Which is a little bit more rich in its structure. Instead of just assuming that we have two groups of neurons that have either identical responses or opposing responses, I will assume something more general. So this will be example 4. And we will assume general GI. I will not assume a particular structure of the GI. And still the same Cij as before. So Cij is A delta Ij plus 1 minus delta Ij alpha. And it turns out that you can write down a nice, relatively nice, well, it's not so nice, but it's a one line, a closed expression for d prime square optimal in this case. So it's just taking the expressions that we had for the optimal discriminability in terms of the inverse matrix of this C and in terms of G, and you can work around using these expressions and reach an expression that I will write down in a moment. And I will just mention that this was done by Maoz Shamir and Chaim Sompolinsky in a paper from 2001. And so I will skip all the details of the calculation and just write down the result. It's not super friendly, but we will analyze it and see that it makes sense. We'll see what it's telling us in some limits. So times minus alpha 1 minus kappa divided by 1 minus alpha times 1 minus n kappa. All this is like this. Oops. Here's the, okay, so we will need it to take a moment to copy it.
What is the assumption of G?
No assumption. So this is completely general. So it's just, you know, we still have assumed is that a particular structure for C, a very particular structure. So if I wouldn't tell you anything, that it means that the noise component in the neurons, first of all, is independent on the stimulus, because the Cij, I mean, this is the whole setup of what we did. There is noise which is independent of the stimulus, and the noise component of the stimulus does not distinguish between the neurons. The Cij is the same for any two neurons which are different from each other, and it's the same on all positions on the diagonal. So from the point of view of the noise, all the neurons are identical to each other. Of course, if I would not assume anything specific for Cij, then the best we can write for d prime opt is the expression that we wrote last time, or maybe it was even last Thursday, I don't remember, which is just in terms of C and G. But now we plug in this particular form of C and work a bit, and that's what we get. Now there are some things here that I didn't yet define. So first of all, what do I mean when I write this bracketed average? I just mean that I will write it in general that for something, the average of X is just 1 over n, the sum over all neurons of Xi. So So square average is just the sum of all the GI squared divided by n. And kappa, which appears here and here, is defined as G square average minus G average square divided by G square average. Now kappa is an interesting, it comes out from working with this expression that you get something like this in terms of kappa, but kappa has a meaning, right? If kappa is 0, what does that mean? It means that the variance across the neurons of G is 0, which actually means that all the G's have to be the same. So if kappa is 0, all the G's are the same. This is the case that we discussed here and here. And turns out that kappa also cannot be larger than 1. So kappa is between 0 and 1. I wonder if it can be 1. Yeah, it can be 1. If the mean, but if kappa, I think the only way kappa can be 1 is if all the G's, the mean. No, it can be. If the mean of G is 0, it can be 1.
Yeah.
Yeah.
But if it's 0, doesn't it mean that they are fully correlated? Not independent? Like if the variance is
No, because this is all kappa has to do with are the G's. The G's are the mean responses. So it means that the mean responses of all the neurons are the same. So, like it has to do with the question of what do we mean when we say correlated and uncorrelated. There are two types of correlations in the neural response. One is generated by the stimulus, and one is given the stimulus generated by the noise. So, given the stimulus, the noise is described by this matrix. It has nothing to do with G. It is true that if G is the same for all neurons, that if you change theta, the neurons will change in a correlated way, right? So it's two different types of things. One is how theta affects the response, and the second, how does the neural variability affect the response. Okay. Anyway, kappa is between 0 and 1. And now let's just look at this expression and see that it gives us things that we already know, and then we'll look at things that we don't know yet. So let's take the case of uniform G. The case of uniform G is the case where kappa is equal to 0. And then if we look at this expression, you see that here you have 0, here you have 0. So you have 1 minus alpha divided by 1 minus alpha, so that cancels. And so you get d prime square is equal to n. And also, if kappa equals to 0, then G, all the neurons have the same G. So instead of the average of G square, I can write G square divided by A times minus times 1 plus alpha times n minus 1. But all this is to the power minus 1. And so you can compare this. I didn't write it explicitly, but you can check. This is exactly the expression that we wrote last time on Tuesday. And so in particular, if alpha equals to 0, we get ng square over a, and if alpha is larger than 0, this saturates as n goes to infinity. This we already did. But what can we say about non-uniform G? So non-uniform G means that kappa is larger than 0. That's all I need. So if alpha is equal to 0, the neurons are uncorrelated. Yes. So if alpha is equal to 0, you see that we have here, okay, one needs to work on it a bit. Let's do it here on the side. If alpha is equal to 0, what do we have here? We have here minus 1
Just
plus...
have 0 because it's multiplied by alpha.
Great. Thank you. Okay. So, yeah, I was thinking more complicated than what it is. Alpha is equal to 0, so just this term falls, and we have ng, still ng square over a. Nothing really mattered. Well, it's not g square anymore. I need to write here n times the average of g square over a. But that's what we have. Okay. And so, for example, note that non-uniform g, this is a particular case of that. Some of them had positive g and some of them had negative g, and in this case g squared was the same for all of them. So in this case, if we would want to use this expression, we would just put here g squared because it's the same for all the neurons. And alpha larger than 0, what do we get? So what I want to ask is just what happens as n goes to infinity. How does this behave? So when n goes to infinity, all I care about is in the denominator is this term, it's term alpha times kappa times n, right? The numerator does not depend on n, but I have an n here. So to leading order, when n is large, I have here 1 minus alpha times 1 over kappa divided by alpha kappa. That's the leading behavior of this term, this whole term. But then I need to subtract from this 1 and take the inverse and then multiply by alpha, add 1, take the inverse. So I will not do the details. You can check them yourself. Eventually what you get is simple. What you get is n times g average squared, actually, which is how g average square comes about. It can come about from combination of kappa and g square average. So, and you end up with this. This I recommend to check yourself that this is true. Times kappa times 1 minus alpha. No, this doesn't make any sense to me. Maybe it's okay. Okay, I'm not sure about this. If the square should be here or here. The reason I suspect that this is wrong is that if we take this case, in this case the average of g is 0 because it's positive for half the neurons, plus g for half the neurons, and minus g for half the neurons, and then we would get here 0, which doesn't make much sense. So this has to be g square average. So let me put here a question mark. I want to make some concluding remarks, so I will leave it for you to check. I think that this is g square, and then if that's the case, you can see how we would recover, I think, the result. By the way, here there was a missing 1 over a. I had this problem also in my last lecture. There was a missing 1 over a. And then you can see that this particular case will agree as because you can see that in this case, case 3, the average of g is 0, so kappa is simply equal to 1. And so here you have 1, and then you can see that you recover the expression that is written there. And g squared is the same for all the neurons. Okay, so now what do we learn from all this? Yes?
Are we left with n in this limit? Because if n goes to infinity, what does it tell us?
Yeah, we are left with n, so that the discriminability increases with the number with the addition of neurons.
Yeah, but n goes
So
to
it's just infinity, no?
Yeah, but you can see how it goes to infinity. So if n is large, so as long as n is, there is some typical n beyond which this is a good approximation for this prime square. So when you write something like this, it tells you much more than just saying that it goes to infinity. It tells you how does it go to infinity. It scales linearly with n. And as a particular case, you see that the result that we got here for two populations with opposing responses agrees with what we got here. But this tells you that this is much more general. That in fact, this case is special. Uniform G is special. For uniform G, you do not improve, you saturate as you add more and more neurons. But as long as there is any variability in the G's, as long as the neurons are not identical to each other in their mean responses, you can improve your discriminability as you increase the number of neurons. And now going back to this geometric picture, you see that if the mean responses lie exactly on the line over which the correlated noise lies on, then as we add more and more neurons, maybe the uncorrelated part of the noise will shrink, but we will remain with this thing which will not allow us to improve our discriminability. But if I would even slightly put these responses off the diagonal, then eventually, if the noise looks like this, I will be able to discriminate without error. So there is one main lesson that you take from all this exercise, which is that if you imagine that the neural variability includes a term which is fully correlated and a term which is uncorrelated, but otherwise all the neurons are identical in the noise part, then it's good to have some variability in the mean responses, to have different mean responses of the different neurons, and then you can get good discriminability. But you can also appreciate that there are many things that we could have imagined more complicated than what we did in this exercise. We assumed here a very specific structure for the noise term. So this is what I want to, just in summary, I want to briefly discuss this and make a few comments. So I will steal a few more minutes from Neta, just so that we can wrap up this topic and move on next week to another topic. So maybe I'll erase this. So I want to make some additional comments. So one kind of broad lesson is both statistics, let's write it different. Both mean structure of mean responses and variability matters. If in particular, components of the variability which are orthogonal to the signal, to the change in the mean responses, don't matter. So the fact, okay, they don't matter. But another comment is that we could have thought of more elaborate scenarios. There are many things that we could have done differently in our discussion. So this is really just an introduction to this topic. We could imagine that correlations are non-uniform, meaning that all neurons are not identical to each other. So for example, you could imagine that there is some spatial structure. There is some, maybe, what do these noise correlations come, where do these noise correlations come from? Maybe they come from some connectivity between the neurons. So maybe some neurons are connected to each other and they're more correlated, or maybe some neurons receive some common input and they're more correlated than others. So this is what I mean by spatial structure. There's another question which comes up a lot in discussion of coding measurement of properties of neural responses in sensory areas, which is perhaps correlations between neurons are related also to their tuning. is this still readable? Yeah, so I will stop here. So, for example, imagine that you look at orientation selective neurons in the cortex. So each neuron, there are many neurons that are, each neuron is selective to some particular angle. Maybe neurons that are selective to similar angles are more correlated in the noise with each other than neurons that are selective to different angles. This is a question that people keep asking, and and the answers are not so clear, not so, even now not so fully, not everyone will agree on them, I think, but this would matter. Okay, so we could have imagined that we have neurons with different preferences, and there is some relationship between the average response and whether two neurons are correlated with each other. Maybe if they have similar average responses, they're more correlated or less correlated than if they have different correlated responses. Then there's another issue that I could have brought up and didn't, which is perhaps in the whole model that I discussed, the noise part was completely independent of the stimulus. We had a mean response, which was dependent on the stimulus, plus noise, which is independent of the stimulus. But we could have imagined that perhaps there are signal-dependent correlations. And if that's the case, then the structure of the correlations themselves is informative about the stimulus. You could imagine, for example, just as in a very extreme case, that imagine that in condition 1, for stimulus 1, all the neurons are fully correlated with each other, and in condition 2, stimulus 2, the neurons are completely uncorrelated with each other. Then you would probably be able to distinguish between the two stimuli by just asking whether the neurons give you the same answer or not give you the same answer, right? So the correlations themselves could carry information about the signal if they depend on the signal. And I would just want to comment that once you do that, so remember that we also discussed a particular type of readout. We discussed only linear readout. So when it turns out that when the correlations are independent of the signal, and we want to do a discrimination task, the linear readout is very good. But when this is the case, maybe a linear readout will not be a good readout. So we would need also to analyze the effect of noise by considering more elaborate readout schemes, maybe the maximum likelihood or some other form. So one last comment is that given all these kinds of analysis, remember that when we talked about tuning curves, we had some part where we talked about what is the best form of a tuning curve of a neuron in order to get high Fisher information, narrow or wide and things like that. So it's tempting when thinking about correlations to bring up similar considerations and say, okay, what is the structure of neural responses and of the variability which will allow us to do well in discrimination or in estimation? And it's an interesting question to ask, but I want to point out that there is something missing in this kind of analysis, or it's important to remember that we neglect something in this analysis, and that is that the correlations between neurons arise from some mechanism. There is some mechanistic reason why neurons are correlated with each other. This might, as I mentioned this earlier, this might have to do with the fact that they're connected to each other recurrently, or it might have to do with the fact that they're receiving some common inputs. It's not always obvious that you can realize that any structure of noise correlation that you might want to obtain can actually be realized. Ideally, you would just want not to have any noise at all in order to have good discriminability. So if there is noise, you have to ask yourself also where is it coming from, and what are the constraints, the mechanistic constraints that are giving rise to this noise. You cannot just imagine any structure of noise that you want. Okay, I think at this point we will finish, and on Tuesday we will start a completely new chapter of the course. Start a new principles of coding. So it's related, but it's a different viewpoint, completely different viewpoint. Yeah. So,
אמרנו שיש סיבות.
so I understand that everyone agrees with Friday morning, what is it?
The ninth.
The 9th or the
ninth.
2nd?
The ninth.
The 9th. Okay. Sure, I'm fine with that. So what time will it be?
I don't know.
You have to, okay, you have to decide on that. So, yeah, okay. I'm sure that some people have made some compromises, so thanks for coming up in a nice way with the solution. For my point, מבחינתי כן. אוקיי, אז חשוב שתשבי ותעשי איזה הפסקה, אבל השיקול הוא, אני אסביר לך את השיקול. במונה יש משהו שהולך לעשות אקספרימנטים תמיד על במונה יש משהו שלא תלוי בהם. במכנה יש בעצם משהו שלא תלוי בהם, פלוס משהו שפחות תלוי בהם. כשאין מספיק גדול, אנחנו נזניח את יש לנו להזניח את השיקול. בעצם אני חושב שמשהו
רק מי שיש לו לינק
עכשיו, האין הזה שאין כזה להתקצר אנחנו נשאר בעצם חלקי אז אני טוען שבגבול שאין הולך לאינסוף הפיתוי הזה הולך לשם עכשיו עדיין צריך להוסיף אז בסוף, אבל תראה שהאין הזה פשוט הוא בא מזה שלא יש כאן בעצם כל מה שכאן הולך לאיזשהו קבוע והוא מוכפל באין נכון, אבל פשוט ההתלבטות כפרשימות של לא, אז חשבתי שאולי זה איכשהו מתבטל אין פה את G, אבל יש פה את קאפה לא, האמת שקאפה הוא כן מכיל את G חשבתי שאולי איכשהו כן, אבל זה לא נראה לי הגיוני נכון
זה לא הביטויים שיעור שעבר, נכון? זה לא ביטוי שפיתחנו פה.
לא.
לרגע חשבתי שוואו, פספסתי משהו.
לא, תפתח את המאמר של שמיר בתוך.
סבבה.